This is a video about electric potential presented by Group A57 with Alyssa, Vivian, Truong-An, Anthony, and Patricia.
So what is electric potential? So electric potential is defined as the potential energy per unit charge of a system. And note that it is specifically electric potential energy as noted by the subscript E in the equation. The SI units of electric potential is in volts, which is also joules per coulombs, as the unit for potential energy is in joules and the unit for charge is in coulombs. From the definition given, we find that electric potential is related to energy. And since energy is a scalar quantity, electric potential is also scalar and not a vector. So this means that there is no direction associated with electric potential. In order to better understand this topic, electric potential is parallel to the principles of gravity. Imagine that you are near the surface of the Earth and there is a block with a mass m. In this example, if the block moves closer to the surface of the Earth, the system loses potential energy as it falls under the influence of gravity. In this example, potential energy does not have direction. Instead, it is just a number associated with the way the system is positioned. This is quite similar to how electric potential works, so I'm going to pass it on to Alyssa to explain more.
Electric potential energy is the energy that is needed to move a charge against its electric field, similarly to how objects have gravitational potential energy as a consequence of its position in a gravitational field. Objects can also have electric potential energy as a consequence of its position in an electric field. If we had a negatively charged plate and a positively charged particle, then the two would attract each other. Placing the positive charge closer to the plate would mean there would be less electrical potential versus a spot at a further location, which would give the charged particle more electric potential energy. In the image below, the topmost positive charge right here is the furthest away from the negative charge. This charge has the greatest electric potential energy as it wants to move closer to this negative plate here. Going back to the first main point that states electric potential or voltage is the potential energy per unit charge of a system. In the image below, we have a negative plate and an imaginary positively charged particle right here. As illustrated, there is less electric potential energy as the charge is closer to the plate in comparison to when it is further from the plate. From the definition, we find that similarly, the electric potential, which is defined as potential energy per unit charge, is also smaller when the positive charge is closer to the negative plate. And this is because the potential energy there is smaller than when it is further from the plate, divided by the imaginary positive charge.
So one important difference between gravitational potential and electric potential is that mass is always positive under gravity, while there are both positive and negative charges in electricity. The example below will help us understand how electric potential is a property of the system and not the charge moving between the locations. So if we had a positive charge set in space and another positive charge moving towards a set charge, we see that the electric potential energy increases as two positive charges repel each other and there is more potential energy to move away from the set charge, and thus potential energy increases as a charge is closer to the set charge. And since we know that the definition of electric potential is the potential energy divided by the unit charge, we find that the difference or change in electric potential is positive, since the potential energy is positive and the charge is also positive. Now, in another example, if we still had the same positive charge set in space, but this time we had a negative charge moving towards the station charge, we would find that potential energy decreases as you move towards the station charge. And to find the change in electric potential, we use the same equation to find that the change in electric potential is also positive because the potential energy was negative and the charge is negative as well. And this just goes to show how electric potential is a property of the system and not the moving charge.
Now that an understanding of electric potential is reached, we can find the electric potential due to a point charge. This is given by the equation right here, 1 over 4 pi epsilon naught times q over r, where q is the charge and r is the distance between the charge and the point. As shown in the equation, a single charge q is needed to calculate the electric potential as it is directly related to electric potential. If a charge is placed at a point, then it will exert a force due to the electric field, and the direction of the electric field is from positive to negative charge. This is important to remember because it affects electric potential depending on the location between the charge and the point.
Where did electric potential originate from? While there isn't an answer that is set in stone, physicist Alessandro Volta was the one to invent the electric battery, which eventually led to the discovery of electric potential. Thus, he is credited for the discovery.
And the first assumption that we have is that electric potential is zero at infinity. And what this is saying is that basically, as the distance between the point and charge increases to infinity, the electric potential is going to be zero, okay? So this is just an assumption. You can assume that electric potential is zero under those circumstances, right? And right here, we have like a graph to kind of represent what this is. You can assume that this is the electric potential is zero as the distance here reach infinity. So eventually they're just gonna keep going to infinity, and that's gonna be the electric potential here, zero. Okay, so we have that was our first assumption, but we have another one.
A common misconception with electric potential is that it has direction. However, in reality, it does not because it is a scalar quantity. So as previously mentioned, electric potential is equal to the electric potential energy over the charge. And with energy being a scalar quantity, electric potential is also a scalar quantity. Because many word problems will talk about moving particles to different locations, whether to the left, to the right, up or down, one might confuse this with the assumption that electric potential actually has direction. However, in reality, the electric potential changes accordingly to however the system is rearranged. This idea is commonly misunderstood due to the confusion with electric field, which is a vector quantity, due to the direction of a force, while electric potential relies on energy. Another misconception is that electric potential can be determined using the charge at the point P, but in reality, it is actually determined by the environment created by the surrounding charges and not the charge at the actual point. So in a problem, one might be given the charge at point P and Q and asked to find the electric potential due to that charge. And in that case, it might be tempting to use Coulomb's law that incorporates both charges into the equation. However, electric potential energy only depends on the surrounding charges and not the charge at the actual point. So with the image on the right, if we were to find the electric potential at the origin, we would find the electric potential of these different points, so V1, V2, V3, and use the principle of superposition to find the electric potential from the point. So in that case, we would add V1 plus V2 plus V3 without actually including the potential at the origin.
Hey, my name is Anthony Vo. I will be presenting the first real-world example today. So our first example is called the electrocardiogram, or ECG for short. And basically, it's a little medical device used in every medical institution. This machine connects a little electrodes onto the surface of the skin and records the electrical activity of the body, mainly around the heart. So each electrode catches a signal that's created through the action potential generated by the individual cells in our body. And this is often used to diagnose heart illnesses and diseases that can't be measured otherwise. So some common illnesses that can be diagnosed using an electrocardiogram are heart attacks, coronary heart diseases, and irregular heart rhythms. The ECG is usually measured in voltage versus time within the heart's electrical activity.